Given three integers n, l, and r, build an array of length n where every value is between l and r inclusive. Adjacent values must differ, and you may not have three consecutive values that strictly climb or strictly fall. Count how many arrays satisfy these rules and give the answer modulo 1,000,007. Example 1, n is 3, l is 4, r is 5. Only 4 and 5 are allowed, and neighbors must alternate. 445 fails because the first two slots match. The two valid zigzag patterns are 454 and 545, so the output is 2. Example 2, L is 1 and R is 3, so each slot has 3 choices. Many triples still break the rules. 1 2 3 is 3 strictly increasing values. 10 arrays satisfy every rule, each valid one appears in the list, so the output is 10. A zigzag array is a constant tug-of-war between two trends, climbing up to a peak, or dropping down to a valley. To solve this efficiently, we don't pick one pattern. We track both trends simultaneously using two parallel grids, one for paths currently heading down, and one for paths currently heading up. At our starting line, index 0, no moves have been made yet. A single number by itself is technically a valid starting path for either trend. So, for every allowed height from 1 to 3, we seed both of our grids with a starting path count of exactly 1. Now we step forward to index 1. To figure out how many paths can climb up to a peak at elevation 3, we have to look back at the opposite trend and manually add up the counts from every single lower height. While doing 1 plus 1 is easy for a height of 3, imagine if our allowed numbers ranged into the thousands. Manually looping and summing all those individual blocks on every single step would make our code incredibly slow. To eliminate this bottleneck, we build a scanning reservoir before we even make our moves. By pre-calculating a running prefix sum from the bottom row up to the top row, our reservoir records the cumulative total of paths available at or below any given height. Instead of running a slow loop to add up individual blocks, we can now look up our answers instantly in a single glance. With our reservoirs filled, calculating our transitions becomes trivial. To find the paths climbing up to elevation 3, we don't write a loop to add up previous slots. We simply peek at the downward trends reservoir at elevation 2, grab that pre-computed total of 2, and drop it straight into our peak tracker. To drop down to a valley at elevation 1, we need the exact opposite, all previous upward paths that are strictly higher than 1. Instead of counting backward, we use a clever math trick. We take the grand total from the very top of our upward reservoir and subtract the lower portion we don't want. The remainder perfectly fills our valley tracker. Step back and see the full dynamic programming picture. Every numbered cell we have been filling is a subproblem. How many valid zigzag paths end at that index and elevation? That is what DP means here. As we march across columns, each next step only reads the previous column and its prefix reservoirs, never the ancient past. So we discard the extra columns and keep exactly 4 one-dimensional arrays in code, DP down, DP up, sum down, and sum up, overwriting them at every index as we slide forward. When the column loop finishes, the last slot of each prefix sum row holds the grand total for that trend. Sum down at index or counts every downward ending arrangement, sum up at index or counts every upward ending one. Add those two summits together, apply modulo to stay safe from overflow, and that is our final answer. We begin by allocating our 4 memory pipelines. To keep our code beautifully pristine, we size our DP arrays to our +1. This allows us to use our actual target numbers as direct index slots, completely avoiding messy index offset math. We stretch our prefix reservoirs to our +2 to create a safe trailing boundary slot at the end. Now we bootstrap our base cases by sweeping across our active range from L to R. Because a single standalone number is a valid path for either direction, every active slot gets an initial count of 1. We immediately accumulate these across our arrays to build our starting prefix sum reservoirs. We kick off our main loop to step through our remaining array positions. For every allowed number j, we update both trends simultaneously. Our peak tracker dp_up looks at the opposite trend's history and grabs the running sum of all strictly lower numbers. At the exact same moment, our valley tracker dp_down subtracts the lower boundary from the grand total to cleanly isolate the count of all strictly higher numbers. With our new step counts established, our old prefix reservoirs are officially outdated. We run a quick, sequential recovery scan from left to right, adding our fresh dp counts into our running totals. This instantly recalibrates our prefix sum pipelines, making them completely ready for the next index iteration. Once our outer loop finishes processing all n array positions, our prefix sum arrays hold the complete history of all valid configurations. We pull the final summits of both our valley paths and peak paths, add them together, apply our modulo arithmetic to protect against integer boundaries, and return our highly optimized final answer. Time scales with the array length times the number of allowed heights. For each extension step we update every height and rebuild both prefix pipelines in one left-to-right sweep. Space scales with the maximum allowed value, for fixed one-dimensional arrays and no recursion stack. Entry: count length n zigzag arrays with every value between L and R inclusive. Set the modulo constant so products never overflow a 32-bit integer. Allocate the valley ending count array with one slot per height up to R. Allocate the peak ending count array with the same direct mapped size. Allocate the valley prefix reservoir with one extra trailing boundary slot. Allocate the peak prefix reservoir the same way. Seed every allowed height before the first extension step. A single value alone is one valid valley ending path at height j. A single value alone is one valid peak ending path at height j. Build the opening valley prefix total through height j. Build the opening peak prefix total through height j. Advance to positions 2 through n in the outer loop. For each allowed ending height j at this array position, valley count equals the peak prefix at R minus the peak prefix at j. Peak count equals the valley prefix strictly below j from the prior step. Copy the leftmost valley count into the refreshed prefix at L. Copy the leftmost peak count into the refreshed prefix at L. Sweep right to fold the new counts into running prefix totals. Each valley prefix slot adds the fresh dp_down count on top of the prior total. Each peak prefix slot adds the fresh dp_up count on top of the prior total. Return the sum of both prefix totals at height R, reduced modulo mod.